Okay, let's start with this second approach that we will discuss for part 1. Okay, the variational approach. Okay, for this one, okay, in this case, we will use this principle of minimum potential energy to apply for this and then derive the finite element equations. Okay, so the to summarize that, I can say that in this procedure, first, you need to formulate the total potential energy of the system or the problem. And after you got the correct total potential energy of the problem, you minimize it. You minimize the total potential energy with respect to the variables or the unknown of the problems. And after that, you would have a function that satisfies the differential equations and natural boundary conditions of the problems. Okay. So what we need to do here, let's say about variational approach. Okay, not going to the FEM. Okay, just yet. Okay, let's say for variational approach, you need to formulate this total potential energy. And after you got this total potential energy, let's say, so we have I here. After you have I, you minimize I with respect to the variables. Okay, so normally to minimize, okay, we normally perform this we call first variation of I, that is the minimize. After that, you would have a function to minimize. Normally we do this del I equal to 0. After that, after this del I equal to 0, what you get is a function that satisfies differential equation of the problem and natural boundary condition. Okay, to do that, you may need a little bit of variational calculus, but don't worry, we're not gonna go into detail or you need to know really advanced variational calculus. No, that's just just some fundamental that's give you a basic things to understand this. That's all. Or maybe just look at the note. It should be okay. Okay, but if you want to know more, then okay, you can just go and look at the content about this in the other sources. But in this case, okay, just follow this. I think it should be okay. So to going with this approach, if the problem doesn't have a relational principle, then it's not applicable. That means you cannot apply this approach to certain problems that do not have relational principle. Okay, most of the problem we have this one, but in certain problem, no. Let's say like some flow problems, certain problems, which of course is not going to be exist in our case. In our case, continuum mechanics problem, I think you would have this one, so no problem. Let's say so no problem in that case. Okay, so let's just see what's happened here. Okay, so in this case, relational calculus that would be adopted here is concerned with finding functions that minimize or maximize. In this case, it's like a minimize integrals, and whose integrands are functional. Oh. So what this is? Functional is a function of function. Okay, it's like this. So this f is functional because it's a function of u, which is also function. Okay, ux is a function, and x would be the independent variables. Okay, so u is a function, and f is a function of u, so it's become functional. Okay, all this f, big F here is also a functional because it's a function of all these things. Okay, u prime and u double prime, these are all function, so this would be functional. So in this case, it's something like we need to minimize some integrals. Okay, let's say you have this some integral I. Okay, and this integral contain functional here. Okay, let's say contain f here. Okay, something like that, and you would have to find a function that's minimize these integrals. Okay, and in this case, x is like an independent variable, so we consider it's fixed. So we do not vary x, we vary ux or u prime x or u double prime x to make the integrals minimum. Okay, so normally it is a function is varying, and in the case that we consider here, the integral will explicitly or implicitly, sorry, contains the differential equations for our problems. So basically, if you have integral I contain function like this, okay, function f like this, and this in our case, f is a function of u, and if you can minimize I here, what you get would be a function u that satisfies our problem. Okay, that satisfies our problem. Okay. So this is like a let's say this is x here, okay, x here, and this is like a some sorry, share this. Okay, so let's say this is a function u. Okay, function u, and u is a function of x. Okay, defined between a and b in here. Okay, and we have this integral I contain function of f here, and f is a function of x, of course, u and also u prime, let's say, and integrate between a and b. So you have u here. This is a function u between a and b. And suppose what we need to do is, if you define or u like this, and we vary u, okay, and see that what is a u that minimum this I. So maybe it's normally when I just like to explain this, I just use this. Let's say, go back to calculus. Function x, right? And have function u x like this, right? And let's say u is like this, okay? And you want to find, maybe it's better, okay? Okay, function u like this. You want to find the minimum value of u over this range. Okay, let's say this between a and b here. You want to find the minimum value of u. What we do is what? We take this, right? U by dx, right? Set it equal to 0, right? And then you can find the value, let's say x0. That give you x0 is minimum, right? Is the minimum value over this range, right? So in this case, when you take this, it means that, okay, slope here is 0, then this would be, let's say, x0, right? So this is what we do in calculus. But in variational calculus, what you do is, say here, you do not integrate, you vary u and see what would give you a minimum value of I. And to do that, we give this symbol del I, okay, equal to 0. Okay, we vary u, okay, because x considered fixed, so we vary u from certain curve into another curve and then another curve and see which curve gives you the minimum value of this I. Okay, so to obtain that one, you have to perform what we call first variation of I and set it equal to 0. Okay, and first variation of I is like this. Let's say, so I is this integral, right? So first variation of I, we can put it like this. Okay, and then you can take this variation symbol inside the integral, okay, and like this, and this equivalent to this, because when you vary, x is considered fixed, so we do not vary. We vary u and u prime. So we vary u and u prime. So this is what you get by performing this first variation. Okay, and from this we integrate the second term here. Okay, by part. Okay, hopefully you still remember by part. Okay, if you I think if you study applied math with me, okay, so you must have at least, you know, try to remember the by part things, right? UV, right? Minus indicate VDU, right? It's like this, right? So you negate the second term here. You define what should be U, what should be V. So this is, I define this U, and V is equal to del of U, right? Oh, I shouldn't use U, right? Because this also okay. Let's do this. Okay, indicate AB, right? Equal to, oh sorry, not AB. Okay, PDQ equal to PQ, right? Indicate QDP, right? So in this case, you define this as a P, and Q would be del U, right? And this is what you get. Just go back here. Okay. So from this, once you do by part, del I would be equal to this. Okay. After doing by part, and from this, for I to be minimum, del I must be 0. Okay. So you have to separate into two things. The first thing is the integral. The second thing is this term. This term defined only at the boundary A and B, right? Because it's not integral. But for the first part, it's integral. So this defines the whole thing. So for this to be 0, first between A and B, okay, coming from the integral, term in the bracket must be 0 because del U should be vary. So you cannot force it to be 0. So that means this term must be 0. Okay. Okay, this is the first term. And then the second term, okay, this term. You have two terms here and here, okay? And this must be 0 at point A and point B. So at point A and B, okay, the term in the bracket must be 0. Then you have two terms. That means either one of them must be 0, okay? The first term or the second term must be 0. So this is what we get by minimizing the integral I here, okay? And as I told you before, after you perform the minimization of I, what you get would be this differential equation for your problem. Okay, if you look at Ajahn, what is the differential equation here? Of course, you're not going to see this because this is just, you know, what I would say is generic formulation. But if you derive the total potential energy of your system, you will see that one. Okay, and I think you can look at the clip later. Okay, you will see. Okay, so for this one is Euler-Lagrange or differential equation of your problem, and then this is the equation that your unknown must satisfy. Okay. So that means this is your unknown U, and you must satisfy this equation. And normally it's a differential equation. Okay. And then these are the conditions at the boundary. So it's the boundary conditions. Okay. If the condition is defined like this form, we call natural boundary conditions. And if it's defined like this form, it's called essential boundary conditions. Okay, essential boundary condition. Okay. If you so the whole thing here for boundary value problem. Okay, boundary value problem for your system. Okay, so normally natural boundary conditions is the condition that associate with you know, traction or force. Okay. Okay. So if you study with Ajahn Charun before, so it's something like that. Okay, and essential boundary condition is the condition that associate with your unknown or displacement. Okay, or displacement. Okay, so if you can really derive, let's say this, as the total potential energy of your system, okay, then in that case, what you get would be here, your equation to be solved and the boundary conditions. So, okay, so this is I think I'm just gonna briefly overview you here. So then you can, you know, follow, you know, going through the video clip, and actually I have 2 clips for this topic, so you can just, you know, and plus this one also 3 actually, so you can go through this one. So let's just, okay,